Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this green shape. And in the second question, we find out the length of this line segment AEP that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have a semicircle. BC equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10 units. PC equals to 8 units. This is angle ABC, that is the right angle. Again, our task is to find out the area of this green shape. So first of all, we'll join points B and P together by straight line. By joining points B and P, we created peripheral angle BPC. Peripheral angle BPC subtends on BC the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So this peripheral angle BPC is the right angle according to rule 5. So I repeat quickly on rule 5. According to rule 5, any peripheral angle that subtends on the diameter of the circle must equal to 90 degrees in its size. So in the drawing, we have a circle. AB is the diameter of this circle. This is peripheral angle AEB that subtends on AB, that is the diameter of this circle. And according to this rule 5, peripheral angle AEB must be equal to 90 degrees in its size. We have already implemented rule 5 in our drawing. In our drawing, we have peripheral angle BPC that subtends on BC, the diameter of this semicircle, and therefore peripheral angle BPC must be equal to 90 degrees in its size according to rule 5. In the next step, we will implement the Pythagoras theorem on the right angle triangle BPC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression of Pythagoras theorem. So according to the Pythagoras theorem, in the right angle BPC, BC is the hypotenuse, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. And again, according to the Pythagoras theorem, in this right angle BPC, BC square, that is the square of the hypotenuse, must be equal to BP square plus PC square. BC is 10, therefore BC square is 10 square, that is 100. And it is equal to BP square. BP is the missing side, so we leave it as it is. BP square plus PC square. PC is 8, therefore PC square is 8 square, that is 64. So in total, we found out that 100 equals to BP square plus 64. Here we subtract 64 from this equation, and we get that 100 minus 64 is 36, so 36 equals to BP square. So here we take a root out of this equation, and we get that BP equals to the square root of 36, that is 6. So we found out that the missing side BP equals to 6 units in its length. This is the missing side BP that equals to 6 units in its length. It is given us the question that AC is a straight line. So if you focus on the left side of the straight line AC at point P, Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angle here at the left side of the straight line is in point P. You have this angle that is right angle, but plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle APB, we define angle BAP. This angle is alpha. So this angle equals to alpha, this angle equals to 90 degrees. And therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. The big angle, angle ABC, is equal to 90 degrees in its size according to what is given as the question. So this is the right angle. Angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle, angle PBC, must be equal to alpha. Why? Because 90 degrees minus alpha minus this angle that is equal to 90 degrees, that is the size of the big angle, minus this angle that is 90 degrees minus alpha, will give us alpha. Or another way, we can say that alpha plus 90 degrees minus alpha equals to 90 degrees, that is the size of the big angle, angle ABC. So therefore this missing angle must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll prove that the right triangle ABP is similar to the right triangle PBC. Why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both right angles and they are both equal to 90 degrees, and therefore they are equal to each other. So if we prove that all the fingers of the right triangle APB are correspondingly equal to all the fingers of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the right triangle ABP is similar, this is the sign of similar, to the right triangle BPC, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle ABP over side BC of the right triangle PBC is equal to side AP of the right triangle ABP over side BP of the right triangle BPC. Actually, side BP or side PB is the common side that belongs to both triangles. And also, it is equal to side PB of the right triangle ABP over side PC of the right triangle PCB. So I repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABP over side BC of the right triangle BPC is equals to side AP of the right triangle ABP over side BP of the right triangle PBC, and it is also equals to side BP of the right triangle ABP over side PC of the right triangle BPC. AB is the missing side, so we leave it as it is. Over BC, BC equals to 10 units in its length, and it is equals to AP, AP is the missing side, so we leave it as it is. Over BP, BP equals to 6 units in its length. Again, BP is equals to 6 units in its length, over PC, PC equals to 8 units in its length, according to what is given as the question. So in total, if we found out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions are equal to each other. Therefore, we get the equation 1 from those two expressions. According to equation 1, we get that AB over 10 equals to 6/8. AB over 10 equals to 6/8. Here we will multiply this equation, equation 1 by 10, and we get that AB equals to 10 times 6 is 60 over 8. So according to equation 1, if we found out that AB equals to 60 over 8. So here we divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, and 8 over 4 is 2. So in total, we found out that the missing side AB is equal to 15 halves. Okay, this is the missing side AB that equals to 15 halves. We continue to focus on the long equation. Those two expressions are equal to each other, so we get the equation 2 from those two expressions. So according to equation 2, AP over 6 equals to 6/8. It again, according to equation 2, AP over 6 equals to 6/8. So here we multiply this equation 2 by 6, and we get that AP equals to 6 times 6 is 36 over 8. AP equals to 36 over 8. Here we divide both the numerator and the denominator of this number by 4. 36 over 4 is 9, and 8 over 4 is 2. So in total, if you found out that AP equals to 9 ounces. AP equals to 9 ounces. So actually, this is side AP that equals to 9 ounce units in its length. In the next step, we define the center of this semicircle. This point is point O. The diameter of this semicircle equals to 10 units in its length, because BC is the diameter that is equals to 10, and therefore the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to 5 units in its length. So the radius BO is 5, the radius OC is also 5. In the next step, we join points P and O together by a straight line. PO is of course the radius of this semicircle that is equal to 5 units in its length. In the next step, we define angle POB. This angle is theta. I will present to you the law of cosines, and we will implement the law of cosines in this triangle BOP. Actually, the law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. This is angle BAC that equals to theta degrees in its size. In this triangle ABC that could be any triangle, the following equation is true. That cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we can actually implement the law of cosines in our triangle POB. According to the law of cosines, in triangle POB, the following equation is true. That cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So actually, this equation is the implementation of the law of cosines in triangle POB. So cosine theta equals to 5 squared. 5 squared is 25 plus 5 squared, that is 25. 25 plus 25 is 50. Minus 6 squared. 6 squared is 36. So this, in the numerator we have in total 50 minus 36 over 2 times 5 times 5. 2 times 5 times 5 is 50. In the numerator we have 50 minus 36 is 14 over 50. So in total we have found out that cosine theta equals to 14 over 50. We'd like to find out the value of theta itself. So how can we find out the value of theta itself? Actually, we have the rule that the inverse function of a function cancels out the action of the function. Again, the inverse function of a function cancels out the action of the function. Okay, so for example, if we have a number 3 and we will operate on number 3 the function square, that is to say the square of 3 is 9. So by operating the function 3, by operating the function square on the number 3, we got the result is 9. Now in order to get back and number 3 again, we just have to operate the opposite function of a square, that is a root, on the result 9. In this way we get back number 3 again. Why? Because the square root of 9 is equal to 3. That is to say, the function, the inverse function of a square, that is the root, cancels out the function of the square. Again, the inverse function of a square, that is the root, cancels out the function of the square. Because by squaring 3, the result is 9. Now, if we operate the inverse function of a square, that is the root, on the result, we get back the number 3 again. So in total, we can say that the inverse function of a function cancels out the action of the function. Okay, so according to this logic, we took angle theta and we operated the function cosine on angle theta. The result is 14 over 50. Now in order to get angle theta again, to get back angle theta again, we just have to operate on the result, the inverse function of cosine. The inverse function of cosine is r cosine. So we'll operate the inverse function of cosine, that is r cosine, on the result, that is 14 over 50. In this way we get back angle theta itself. Okay, so, and we know, we can find out in any scientific calculator that r cosine of 14 over 50 is equal to 73.74 degrees. So if you found out that angle theta equals to 73.74 degrees in its size. So this is angle theta, is equals to 73.74 degrees in its size. So our task is to find out the area of this green shape. In order to find out the area of the green shape, we have to find out first of all the area of this segment BP. So what is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP is equal to the area of sector BOP minus the area of triangle BOP. So write it down. The area of this segment BP is equal to the area of sector BOP minus the area of this triangle BOP. repeat again, we found out hopefully the area of segment BP equals to the area of sector BOP minus the area of triangle BOP. So, what is a sector? A sector is a portion of a circle with two radii and the angle between them. Repeat again. The green shape is sector AOB. Sector AOB consists of two radii and the arc AB between the two radii. This is angle theta, this is the angle between the legs of sector AOB. And the area of the sector AOB is equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So we can implement the new rule in order to find out the area of this sector, sector BOP. This is angle theta. We have only found out that the size of angle theta is 73.74 degrees in its size. BO is the radius of the semicircle, that is 5. OP is also the radius of the semicircle, that is equal to 5. So the area of this sector BOP will be equal to pi r squared times the angle between the legs of the sector, that is 73.74 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi times 73.74 degrees over 360 degrees. So the value of this expression in total is equal to 16.088 square units. So if you found out that this sector BOP is equal to 16.088 square units in its size. What is the area of this triangle BOP? PO equals to 5. PO equals to 5, and therefore triangle BOP is an associated triangle. We already found out that BP equals to 6 units in its length. So in order to find out the area of this associated triangle BOP, BP is the base of the associated triangle BOP. So in order to find out the area of this associated triangle, from the vertex O, we go perpendicular on the base BP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in the base BP. This point is point M. We have the rule that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So the perpendicular OM to the base PB bisect the base PB. PB is 6, therefore half of it is 3. So the first half is PM, that is 3, and the second half is MB, that is also 3. So in the right triangle MPO, 5 squared equals to 3 squared plus MO squared, according to the Pythagoras theorem. Here we subtract 3 squared from this equation, and we get that 5 squared minus 3 squared equals to MO squared. So MO squared equals to 5 squared is 25, minus 3 squared, that is 9, 25 minus 9 is 16, so 16 equals to MO squared. Here we take a root out of this equation, and finally we get that MO equals to the square root of 16, that is 4. The height MO equals to 4 units in its length. Now it is very easy to find out the area of this associated triangle BOP. And according to the rule that the area of any triangle equals to the base of the triangle times the height over 2. The base is BP, we will choose the base as BP, times the height MO. Why MO is the height? Because it's greater 90 degrees with the base BP. Times the height MO over 2. BP is 6. MO is 4 divided by 2. 4 over 2 is 2 and 2 times 6 is 12. So in total we found out that the area of this associated triangle BOP is equal to 12 square units. So in total the area of segment BP will be equal to 16.088, that is the area of the sector, minus the area of this associated triangle, that is 12 square units. 16.088 minus 12 is 4.088. So in total we found out that the area of this segment BP is equal to 4.088 square units in its size. Okay, again, I should found out that the area of this segment BP is equal to 4.088 square units in its size. Our test is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see that the area of this green shape equals to the area of the right triangle PAB minus the area of this segment BP. The area of the green shape equals to the area of the right triangle ABP minus the area of this segment BP. So if it again, we should find out that the area of the green shape is equal to the area of the right triangle APB minus the area of segment BP. What is the area of the right triangle ABP? It is actually equals to the base of the triangle times the height over 2. The base is so the base is AP times the height, that is PB over 2. AP is 4.5. BP is 6 over 2. 6 over 2 is 3, and 3 times 4.5 is 13.5. If you found out that the area of this right triangle ABP is equal to 13.5 square units in its size. Minus the area of this segment BP. We already found out that the area of segment BB equals to 4.088 square units and 14.5 minus 4.088 is equal to 9.412 square units. So if you found out that the area of the green shape, that is the area that we are looking for in this question, is equal to 9.412 square units in its size. That is the answer to the first question. And again, we should find out that the area of this green shape is equal to 9.412 square units in its size. Okay, so we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question by using two different methods. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. AB equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10 units. BC, line segment BC equals to 6 units in its length. AP equals to PC equals to x. Again, our test is to find out the length of line segment AP is equals to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. The diameter of this semicircle AB equals to 10, therefore the radius must be equal to 5. The radius OA is 5. The radius OB is also 5. In the next step, we join points P and O together by a straight line. Point O is the center of the circle, point P is the point of the semicircle itself, therefore PO is the radius of this semicircle, this is equal to 5 units in its length. By doing all those constructions, you get the deal. The associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because side AO equals to side OP equals to 5. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in the right triangle, in the associated triangle APO, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as theta, then the size of this angle must be also equal to theta because they are equal to each other. They are located in front of those two equal sides, therefore they are equal to each other. So in this associated triangle AOP, theta plus theta is 2 theta, and therefore this vertex angle must be equal to 180 degrees minus 2 theta. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle APC, what triangle APC is an associated triangle because side AP equals to side PC equals to x. X is line segment that we're looking for in this question. So in this, the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But we have already found out that the size of this angle is theta, therefore the size of this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. So in the big associated triangle APC, theta plus theta is 2 theta, and therefore this first missing angle must be equal to 180 degrees minus 2 theta according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy the big associated triangle APC in the small associated triangle AOP in a new page, and we prove that those two associated triangles are similar to each other according to angle similarity rule. But before that, what is the length of side AC of the associated triangle ABC? AC in total equals to 10 plus 6, that is 16. So the length of side AC of the big associated triangle ABC is equals to 16 units. So actually, those are the two isosceles triangles that I copied from the original drawing. This is the big isosceles triangle, triangle APC. This is the small isosceles triangle, triangle AOP. So we prove that those two isosceles triangles are similar to each other according to angle similarity rule. So why those two isosceles triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 theta, therefore they are equal to each other. In addition, those two angles are both equal to theta, and therefore they are equal to each other. And finally, those two angles are both equal to theta, and therefore they are equal to each other. So if you found out that all the angles of the big isosceles triangle, triangle APC, are correspondingly equal to all the angles of the small isosceles triangle, triangle AOP, and therefore those two isosceles triangles are similar to each other according to angle similarity rule. So write it down. So if you found out this big isosceles triangle, triangle APC, is similar, this is the sign of similar, to the small isosceles triangle, triangle AOP, according to angle similarity rule. And for the fact that those two isosceles triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of the big isosceles triangle, triangle APC, over side AP of the small isosceles triangle, triangle AOP, is equal to side PC of the big isosceles triangle, triangle APC, over side PO of the small isosceles triangle, triangle AOP. So again, from the fact that those two isosceles triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AC of the big isosceles triangle, triangle APC, or side AP of the small isosceles triangle, triangle AOP, equals to side PC of the big isosceles triangle, triangle APC, or side PO of the small isosceles triangle, triangle AOP. AC is 16, over AP is X, and it is equals to PC. PC is also X, over PO is 5. So in total, we should find out that 16 over X equals to X over 5. Here we cross multiply this equation, and we get that X times X is X squared equals to 16 times 5. So X squared equals to 16 times 5. Here we take a root out of this equation, and finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. 4 times square root of 5 is 8.94. So in total, if you found out that AP is equal to X, is equal to either 4 times square root of 5 units in its length, or in terms of numbers, AP is equal to X is equal to 8.94 units in its length. Repeat again, if you found out that the length of this line segment AP is equal to X, it is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equal to X is equal to 8.94 units in its length. So we finished the first method. In the next step, I will present to you how to find out the length of this line segment AP that is equal to X according to the second method. In the second method, we use the rule that we have already used in the first question. According to the rule, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. Triangle, the big triangle, triangle APC is an associated triangle because of the fact that AP equals to PC equals to X. The base of this associated triangle, triangle APC is AC. AC, the base AC equals to 10 plus 6, that is 16. AC equals to 16 units in its length, and it is the base of the associated triangle, triangle APC. AC equals to 16 units in its length. So, from the vertex P of the associated triangle, triangle APC, we draw perpendicular on the base AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC. This point is point M. According to the rule that I mentioned, the perpendicular PM to the base AC bisects base AC. AC in total is 16, so each half must be equal to 8. The first half AM is 8. And the second half of AC, that is MC, it is also equals to 8 units in its length. So, in the next step, we'll define the center of this semicircle. This point is point O. And we'll join points O and P together by straight line. Point O is the center of the circle, point P is the point of the semicircle itself. Again, point O is the center of the semicircle, point P is the point of the semicircle itself. Therefore, OP is the radius of this semicircle, that is equals to 5 units in its length. What is the length of the small line segment? Line segment OM. From the drawing, it is very easy to see that OM in total equals to AM minus AO. Again, OM equals to AM minus AO. So I write it down. The length of the short line segment OM is equal to AM minus AO. So OM equals to AM. AM equals to 8 minus AO, that is 5. AO is the radius of the semicircle, that is equals to 5 units in its length. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. The short line segment OM equals to 3 units in its length. So in the next step, we'll implement the Pythagoras theorem on the small right triangle POM in order to find out the length of the missing side PM. So I copy the right small triangle POM in a new page and we'll implement on it the Pythagoras theorem. The hypotenuse PO equals to 5 units in its length, OM equals to 3 units in its length. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the small right triangle PMO that according to the original drawing, according to the Pythagoras theorem, this right triangle POM, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. So I write it down. PO squared, that is the square of the hypotenuse, is equal to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equal to PM squared. PM is the missing side, so we leave it as it is. So PM squared plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we found out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation, and we get that 25 minus 9 is 16 equals to PM squared. So here we take a root out of this equation, and finally we get that PM equals to the square root of 16, that is 4. So actually, this is the missing side PM, that equals to 4 units in its length. So in the next step, I'll copy the right big triangle APM in a new page, and we will implement on it the Pythagoras theorem. The hypotenuse AP equals to x units in its length. That is the line segment that we are looking for in this question. AM equals to 8 units in its length, and just right now found out that PM equals to 4. Here by PT is the progression for Pythagoras theorem. So actually, this is right triangle APM that according to the original drawing, according to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. So I write it down. AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. AP is x, therefore AP squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. 16 plus 64 is 80. So if you found out that x squared equals to 80, here we substitute 80 by 16 times 5, so x squared equals to 16 times 5. Here we take a root out of this equation, and we get that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only 5. 4 times square root of 5 is 8.94 units. So actually, in both methods, we found out actually that the length of this line AP is equal to x. It is equal to either 4 points square root of 5 units, or in terms of numbers, it is equal to 8.94 units. Again, we found out in both methods that the length of this line segment AP is equal to x. It is equal to either 4 times square root of 5 units in its length, or in terms of numbers, AP is equal to x is equal to 8.94 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. in the first question, our test is to find out the area of this ring shape. So in the drawing, we have a semicircle. BC equals to 10 units in itself. That is to say, the diameter of this semicircle is 10. Therefore, the radius equals to 5. In addition, we know that PC equals to 8 units in itself. Again, our test is to find out the area of this ring shape. So first of all, we join points B and B together by a straight line. By joining points B and B, we create a peripheral angle BPC. Peripheral angle BPC subtend on BC, that is the diameter of the semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or circle must be equal to 90 degrees in its size. Therefore, according to rule 5, peripheral angle BPC equals to 90 degrees in its size. In the next step, we implemented the Pythagoras theorem on the right triangle BPC. According to the Pythagoras theorem, in a right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. The hypotenuse of the right triangle BPC is BC, therefore the score of the hypotenuse is BC square, and BC square equals to BP square plus BC square. Repeat again, the right triangle BPC according to the Pythagoras theorem, the following equation is true. Then BC square, that is the score of the hypotenuse, equals to BP square plus PC square. BC is 10, therefore BC square is 10 square, that is 100, plus BP square. BP is the missing side, so we leave this it is, plus PC square. PC is 8, therefore PC square is 8 square, that is 64. So in total, we found out that 100 equals to BP square plus 64. Here we subtracted 64 from this equation, and finally found out that BP square equals to 100 minus 64 is 36. So BP square equals to 36. Here we took out of this equation, and finally found out that BP equals to the square root of 36, that is 6. So this is the missing side BP, that equals to 6 units in its length. It has given us the question that AC is a straight line. So if we focus on the left side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. According to rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AC at point B? We have this angle that is the right angle, plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right triangle APB, we define angle BAP, this angle is alpha, this angle equals to 90 degrees. Therefore this third missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees, that is the sum of the angles in any triangle. It is given as a question that the big angle ABC, this angle is a right angle, it is equal to 90 degrees in its size. We already found out that angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle PBC must be equal to 90 degrees minus 90 degrees minus alpha. 90 degrees minus alpha is alpha. Or in other way, you can say that alpha plus 90 degrees minus alpha is 90 degrees, that is the side of the big angle ABC. Therefore, this missing angle must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the right triangle APB is similar to the right triangle BPC according to angle similarity. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you found out that all the figures of the right triangle ABP are correspondingly equal to all the figures of the right triangle PBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And again, after we found out that the right triangle ABP is similar, this is the sign of similar to the right triangle BPC according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right angle ABP over side BC of the right angle PBC is equal to side AP of the right angle ABP over side BP of the right angle PBC, and it is also equal to side BP of the right angle APB over side PC of the right angle PBC. Okay. Repeat again, we derive that side AB of the right angle ABP over side BC of the right angle BPC equals to side AP of the right angle ABP over side BP of the right angle BBC, and it is also equals to side BP of the right angle ABP over side PC of the right angle PBC. AB is the missing side, so we need to sit it over BC. BC is 10 according to what is given in the question, and it is equals to AP. AP is the missing side, so we leave it as it is over PB. PB is 6, and it equals to PB, that is 6, over PC. PC is 8. So in total, we found out that AB over 10 equals to AP over 6 equals to 6/8. Those two expressions are equal to each other, so we can get the first equation from those two expressions. That is to say, according to the first equation, AB over 10 equals to 6/8. AB over 10 equals to 6/8. We multiplied this equation by 10 and found out that AB equals to 10 times 6, that is 60 over 8. Yeah. AB equals to 60 over 8. Here we divided both the numerator and the denominator of this number by 4 and found out actually that 60 over 4 is 15 and 8 over 4 is 2. So total we found out that the length of AB is 15 halves. We continue to focus on the long equation. This is the long equation, so those two expressions are also equal to each other, therefore we get the second equation from those two expressions. So according to the second equation, AP over 6 equals to 6/8. And again, according to the second equation, AP over 6 equals to 6/8. Here we multiply this equation 2 by 6 and found out actually that AB equals to 6 times 6, that is 36/8. Here we divided both the numerator and the denominator of this number by 4. 36 over 4 is 9 and 8 over 4 is 2. So in total we found out that AP equals to 9 halves units in its length. This is the missing 9/7 AP, this equals to 9 halves units in its length. In the next step, actually we know that the diameter of this semicircle is 10, therefore the radius BO is 5, the radius OC is also 5, and the radius PO is also 5. In the next step, we define angle POB, this angle is theta. Then I presented to you the law of cosines, and we implemented the law of cosines in this angle POB. The law of cosines is true in any triangle. So actually, this is triangle ABC that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is an angle BEC that equals to theta degrees in size, according to our definition. So, in this triangle ABC that could be any triangle, the following equation is true. That cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. In the next step, we implemented the law of cosines in this triangle POB. According to the law of cosines, in this triangle POB, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. Okay, again, according to the law of cosines, in this triangle POB, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. 5 squared is 25 plus 5 squared is 25, 25 plus 25 is 50, minus 6 squared, that is 36. So in the numerator in total we have 50 minus 36, that is 14. in the denominator we have 2 times 5 times 5, that is 50. So in total, we should find out that cosine theta equals to 14 over 50. Cosine theta equals to 14 over 50. We would like to find out the value of theta itself. We should operated the function cosine on an angle theta, and the result is 14 over 50. So how can we find out the value of theta itself? In order to find out the value of theta itself, we use the rule that says that the inverse function cancels out the operation of the function. Again, the inverse function cancels out the operation of the function. We know that the square is the root is the opposite, is the inverse function of a square. Again, the root is the inverse function of a square. So if we take number 3 and we will operate the function square on it, that is to say, we will square 3 squared is 9. So the result of the operation square on number 3 is 9. Now, in order to get back number 3 again, we just have to operate the opposite function of a square on the result, that is 9. In this way, we get number 3 again. So the opposite, the inverse function of a square is a root. So the root of 9 is 3. That is to say, the inverse function that is of a square that is a root cancels out the action of a function. So in order to find out the value of theta itself, we just have to operate the opposite function of a cosine that is r cosine on the result that is 14 over 50. In this way, we get back angle theta itself. So the opposite function, we operated it on the result 14 over 50. And this will give us angle theta back. That is to say, r cosine of 14 over 50 equals to theta. We know that r cosine of 14 over 50 is 73.74 degrees in size. Actually, we can find out the value of r cosine by using any simple scientific calculator. So r cosine of 14 over 50 is equals to angle theta, and angle theta equals to 73.74 degrees in its size. So if you found out that this is angle theta, and the size of this angle theta is 73.74 degrees. Okay. Our task is to find out the area of this green shape. In order to find out the area of this green shape, we have to find out the area of this segment BP. So what is the area of segment BP? Actually, the area of segment BP equals to the area of sector BOP minus the area of triangle BOP. Okay, repeat again, the area of segment BP equals to the area of sector BOP minus the area of this triangle BOP. The area of segment BP is equal to the area of sector BOP minus the area of triangle BOP. What is a sector? A sector is a portion of a circle with 2 radii and the arc between them. And again, the green shape AOB is a sector. Sector AOB consists of 2 radii and arc AB that is between the 2 radii. Angle theta is the angle between the 2 radii, or the angle between the legs of the sector. The area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. Okay, so we use the new formula in order to find out the area of this sector, sector BOP. According to the new formula that I presented to you, the area of this sector BOP must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 73.74 degrees over 360 degrees. R is 5, it is the radius of the semicircle that is 5, therefore R squared is 5 squared, that is 25. Pi R squared is 25 pi times 73.74 degrees over 360 degrees. The value of this expression in total is equal to 16.088 square units. So if you found out that the area of this sector BOP equals to 16.088 square units in its size. Now we have to find out the area of this triangle POB. First of all, triangle POB is an associated triangle. Why? Because PO equals to OB equals to 5. You know that in this associated triangle POB, PB is the base of the associated triangle. And we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. From point O, we draw perpendicular on the base PB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and PB, the base PB, this point is point M. According to the rule that I mentioned, the perpendicular OM to the base PB bisect base PB. PB is 6, therefore each half must be equal to 3. MP is 3 and MB is also 3. Now we implement the Pythagoras theorem on the right triangle PMO. According to the Pythagoras theorem, in this triangle, right triangle PMO, 5 squared equals to 3 squared plus MO squared. Again, 5 squared equals to 3 squared plus OM squared. 5 squared is 25, minus 3 squared is 9. We subtract 9 from this equation. 25 minus 9 is 16. So in total we should find out that 16 equals to OM squared. Here we took root out of this equation and found out that OM equals to the square root of 16, that is 4. The height OM is 4. Now it is very easy to find out the area of this associated triangle POB. According to the rule that the area of any triangle equals to the base of the triangle times the height to the base over 2. The base is PB, the height is OM divided by 2. Why the height is OM? Because it's creates 90 degrees with the base PB. PB is 6, OM is 4 divided by 2. 4 over 2 is 2 and 2 times 6 is 12. So in total we should find out that the area of this associated triangle POB is equal to 12 square units in its size. And the area of this segment BP equals to the area of this sector POB, that is 16.088 square units, minus the area of this associated triangle POB, that is 12 square units. So 16.088 minus 12 is 4.088. So in total we should find out the area of this segment BP is equals to 4.088 square units in its size. Our task is to find out the area of this green shape. From the drawing it is very easy to see the area of this green shape equals to the area of the right triangle APB minus the segment BP. Repeat again, the area of the green shape in total is equals to the area of the right triangle APB minus the area of segment BP. What is the area of this right triangle APB? It is equals to the base AP times the height PB over 2. AP times PB over 2. AP is 4.5, PB is 6 over 2. 6 over 2 is 3, and 3 times 4.5 is 13.5. So in total we should find out that the area of this right triangle APB is equals to 13.5 square units in its size. Minus the area of this segment BP. We already found out that the area of segment BP equals to 4.088 square units in its size. And 14.5 plus 4.088 is 9.412 square units in its size. In total, if you found out that the area of this green shape that is there that we are looking for this question is equals to 9.412 square units in its size. We finish with the first question. In the next step, I presented you the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the length of side line segment AP is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. AB equals to 10. That is to say the diameter of this semicircle equals to 10, therefore the radius is 5. In addition, we know that line segment BC equals to 6 units in itself. AP equals to PC equals to x. AP is the line segment that we are looking for in this question. First of all, we define the center of this semicircle. This point is point O. OA is the radius that is 5. OB is also the radius of this 5. We join points O and P together by side line. OP is also the radius of this semicircle is equals to 5. By doing all those constructions, we get that the associated triangle APO. Why triangle APO is an associated triangle? Because OP equals to OA equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. So in triangle, the associated triangle APO, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as theta, then the size of this angle must be also equal to theta because they are equal to each other. Theta plus theta is 2 theta, therefore this angle must be equal to 180 degrees minus 2 theta, that is the sum of the angles in an triangle. Likewise, in the big associated triangle APC, why triangle APC is an associated triangle? Because AP equals to PC equals to X. So in the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But we have only found out that the size of this angle is theta, therefore the size of this angle must be also equal to theta because they are equal to each other. So in the big associated triangle APC, theta plus theta is 2 theta, and therefore this angle must be equal to 180 degrees minus theta, 180 degrees minus 2 theta, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copied the right big associated triangle APC and the small associated triangle AOP in the new page, and we proved that those two associated triangles are similar to each other according to angle similarity rule. So those are the two associated triangles that are going from the original drawing. This is the big associated triangle APC, and this is the small associated triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 theta, therefore they are equal to each other. In addition, those two angles are both equal to theta, therefore they are equal to each other. And finally, those two angles are both equal to theta, therefore they are equal to each other. So if you prove that all the angles of the big associated triangle APC are corresponding equal to all the angles of the small associated triangle AOP. Therefore, those two associated triangles are similar to each other according to angle similarity rule. The big associated triangle APC is similar. This is the sign of similar to the small associated triangle AOP according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we know that the following relationship exists between their sides. First of all, AC in total equals to 10 plus 6, that is 16. AC equals to 16 units in itself. From the fact that those two associated triangles are similar to each other, we know that the following relationship exists between their sides. We know that side AC of the big associated triangle APC over side AP of the small associated triangle APC is equals to side PC of the big associated triangle APC over side PO of the small associated triangle AOP. AC is 16, AP is X, PC is also X, over PO. PO is 5. So in total, if you found out that 16 over X equals to X over 5. Here we cross multiply this equation, and finally found out that X times X is X squared equals to 16 times 5. Here we took a root out of this equation, and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only 5. So in total, X equals to 4 times square root of 5 units in its length. 4 times square root of 5 is 8.94. So in total, if you found out that the length of this line segment AP is equals to X, it is equals to either 4 times square root of 5 units, or in terms of numbers, AP is equals to X equals to 8.94 units in its length. We finished with the first method. In the next step, I presented to you how to find out the length of line segment AP is equal to X by using a second method. In the second method, we use the rule that we already used in the first question. The rule states that the perpendicular to the base of an associated triangle bisect the base. Again, the rule states that the perpendicular to the base of an associated triangle bisect the base. The big triangle APC is an associated triangle because AP equals to PC equals to X. The base of the associated triangle APC is AC. AC equals to 10 plus 6, that is 16. So, according to the rule that I mentioned, from the vertex P, we go perpendicular on the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point P and AC. This point is point M. So, according to the rule that I mentioned, the perpendicular PM to the base AC bisect base AC. AC in total is 16, therefore each half must be equal to 8. The first half AM is 8, the second half MC is also 8. So, point O is the center of the circle. Therefore, OA is the radius of the circle, that is 5, because the diameter is 10. PO is also the radius of the circle, that is 5. So what is the length of the small line segment OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. AM is 8 minus AO. AO is 5. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. So in the next step, I copied the small right triangle POM in a new page, and we implemented the Pythagoras theorem on this small right triangle POM. Okay, this is the small right triangle POM that I copied from the original drawing. According to the Pythagoras theorem, in this small right triangle POM, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, plus PM squared. PM is the missing side, so we leave it as it is. Plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total, we should find out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation, and we found out that PM squared equals to 25 minus 9 is 16. Here we took out of this equation, and we found out that PM equals to the square root of 16, that is 4. So actually, this is the missing side PM, this equals to 4 units in its length. In the next step, I copied the right base triangle APM in a new page and implemented on it the Pythagoras theorem. This is the right base triangle APM that I copied from the original drawing. AP equals to X, that is the line segment that we are working on in this question. PM equals to 4 and AM equals to 8. According to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. AP is X, therefore AP squared is X squared, and this equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total, X squared equals to 16 plus 64, that is 80. X squared equals to 80. Here we substitute 80 by 16 times 5, so X squared equals to 16 times 5. Here we took out all those equations and found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. 4 times square root of 5 is 8.94 units. So in total, in both methods, found out that the length of line segment AP is equal to X. It is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equal to X is equal to 8.9 units in its length. Okay, thank you very much.